Welcome back to Honors Calculus. In this video, we're going to finish up our discussion of the derivative with a bit of work on vertical asymptotes and vertical tangent lines. These ideas will let us round out the concept of the limit and also extend the idea of tangent lines to lines that have undefined slope, vertical lines. So let me get my head out of the way and let's get started. Let's look at a definition where we have some real valued function of one real variable f and some arbitrary real constant c. We say that the limit of f of x as x approaches c tends towards infinity. Notice here that the idea is tends towards infinity. The idea here is not equals infinity. Infinity is not a number. So we can't set anything equal to infinity, but we can say that the function is going infinite in a more colloquial sense. We can say that the limit tends towards infinity if and only if for all m greater than 0, not epsilon, but a capital M in this case. But then it continues on the same. There exists a delta greater than 0 such that whenever 0 is less than the absolute value of x minus c is less than delta, instead of absolute value of f of x minus L less than epsilon, we get that f of x is strictly greater than m. So instead of trying to form our bounding box the way we did for a normal limit, when we say that the limit tends towards infinity, what we're trying to say is that no matter how big you go, you can narrow the region around the point and the function goes even bigger. The simplest example of a function where the limit tends towards infinity is f of x equals 1 over x squared. When f of x is 1 over x squared, the graph of y equals f of x looks something roughly like that. Right? On the left or on the right, this function goes very quickly, very large. And it has a vertical tangent line at y equals 0. If you evaluate the function at x equals 0, then there is no value. Right, so we know from our previous study of algebra that this function has a vertical tangent line when x is equal to 0. Our goal, as has been our goal all unit, is to try to analyze a little bit more closely what exactly it means to have a vertical tangent line. And so we want to study the limit as x approaches 0 of 1 over x squared. We try our shortcut. If we can just evaluate the function at the point, we can cross our fingers and hope that everything works out. In this case, we get 1 over 0, which is undefined. All right, so that didn't quite work out. And in fact, whenever we have 1 over 0, whenever we have anything over 0, a point where the limit is undefined, we're going to end up with a vertical asymptote at that point. Whether or not the limit tends towards infinity or tends towards negative infinity, or the third case of the limit is actually does not exist, whenever we have this x over 0 where x is non-zero, right? In this case, 1 over 0, that is always going to correspond to a vertical tangent line. The 0 over 0 case is the case where the discontinuity might be removable. When we don't have the indeterminate form, then we are stuck with a vertical tangent line. But analyzing this a little bit closer, the definition of infinite limit says pick an m greater than 0. So let's pick a value of m. Maybe 10,000. Notice that the square root of m, or actually let's just go ahead and plug this in, 1 over x squared is 10,000. That means that x squared is 1 over 10,000, or x is the square root of that, plus or minus 1 over 100. Whenever x is inside that range between negative 1 over 100 and positive 1 over 100, the value of the function is bigger than 10,000. If we try a larger number, right? 10,000 just didn't cut it, so let's try something bigger. $1 million. Well, instead of 10,000 here, we have 1 million. And the square root of 1 million, or the square root of 1 over 1 million is plus or minus, which I don't have to write twice, 1 over 1,000. And if we really wanted to, we could go bigger. Right? If I tried m being something ludicrously large, 10 to the 80th power. I really like the number 10 to the 80th power. Some models of the universe predict that there are something in the order of 10 to the 80 particles in the universe. That's it. And in those models, numbers bigger than 10 to the 80 don't have a lot of useful meaning. Right? In mathematics, we don't worry so much about whether or not the number has a physical meaning. We just care about, can we do things with it? But if we set m equals 10 to the 80, we can set 1 over x squared to get that x is plus or minus 10 to the negative 40. Again, ludicrously small number. Does it have any meaning in reality? Actually, yeah, as small as that number is, there is some way of approaching it. 10 to the negative 40 is a bigger number than the likelihood of shuffling a deck of playing cards and ending up with the cards in exactly the standard order, suit in order, ace through king on each suit. That's something in the ballpark of 10 to the negative 60. Great. But this is numerically what we're talking about when we talk about something having an infinite limit. And when we look at an infinite limit, we also can look at things going in the negative direction. If I took the negative of this function, it would flip everything upside down, and that's perfectly fine. And so to have the limit as x approaches c of f of x tend towards negative infinity, we just have to switch a couple of inequality signs. Instead of picking an m bigger than 0, we instead want to pick an m less than 0. And instead of f of x being greater than n, we want f of x to be less than m. Other than that, same definition, same approach. When it comes to rational functions, it turns out that if the multiplicity of the discontinuity in limit after you reduce things is even, then you will have a limit tending towards infinity or negative infinity. If the multiplicity is odd, you'll not have that, and instead you'll have a limit that does not exist. We're not going to worry too closely at the moment whether the limit exists or not. Instead, we're just going to be looking at this as a way of looking for vertical asymptotes. So for example, we might want to classify the discontinuities of the function f of x equals x minus 2 over x squared minus 4 as either removable or asymptotic. There's a third kind of discontinuity, a jump discontinuity. I didn't bother to write that down because jump discontinuities cannot happen in algebraic functions. They can and will happen in piecewise defined functions, and we've looked at a couple of piecewise defined functions that had jump discontinuities. But asymptotic discontinuities are the other kind of essential discontinuity that we can look at here. So we look at the discontinuity starting off the same way you would in an algebra course. We take the denominator, x squared minus 4. We claim that it must not be 0, which means that factoring x squared minus 4, that's x plus 2 times x minus 2. And the only way for the product of two things to be non-zero is to make sure that none of the things you're multiplying are 0. So x plus 2 is not 0. And x minus 2 is not 0, which means that x is not negative 2. And x is not positive 2. To classify these discontinuities, we can look at the limit. The limit, as x approaches 2, of x minus 2 over x squared minus 4. The big idea that we looked at with limits is that when you have a fraction, you can reduce the fraction, right? Any two functions that agree everywhere except possibly at the point of interest for the limit have equal limits. So if I try evaluating x equals 2 here, I get 0 over 0, the indeterminate form. When I have the indeterminate form, I try reducing the fraction. Right? X squared minus 4 factors to x plus 2, x minus 2. And the x minus 2's can cancel each other out, leaving me with the limit as x approaches 2 of 1 over x plus 2. And here, if I evaluate, I get 1/4. As soon as I can get a number out, I've found my limit. So as x approaches 2, we have a discontinuity, but the limit exists, which means that the discontinuity is removable. As x approaches -2, of our function x minus 2 over x squared minus 4, if I tried plugging this in, I would get -4 over 0, which is undefined. Right? I could look further to determine if this limit exists, does not exist. Right? The limit could be infinity, it could be negative infinity, it could just simply not exist. But no matter what, as soon as I find this something over 0 undefined form, I can say right away that the function has a vertical asymptote at x equals -2. All right, that's all well and good, but I said vertical tangent lines. And vertical tangent lines occur when the derivative, which is defined as a limit, tends towards infinity or negative infinity. So here is where we have to start looking at things a little bit more closely. A classic example of a vertical tangent line is the function f of x equals the cube root of x. So if we want to find the tangent line, or the line tangent to the curve y equals the cube root of x at the point x equals 0, we want to use the limit definition of the derivative. F prime of 0 is the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. All right, f of x is the cube root of x. F of 0 is the cube root of 0, which is 0. So we end up with the cube root of x over x, which is x to the negative 2/3 power. Right, that's That's me being a horrible mathematician. Let's try writing this out again without me being a horrible mathematician. And include that I'm still taking the limit as x approaches 0 in every single one of those steps. That is kind of important. But again, this fraction does reduce. Right? The cube root of x is x to the 1/3 power. And subtracting or dividing like bases, you subtract the exponents. 1/3 minus 1 is -2/3. So you get x to the -2/3, or 1 over x to the 2/3. Which is 1 over 0 undefined. Now, a tangent line need not be defined. There are places, there are situations where the tangent line simply is undefined. But when the function is defined and the tangent line does something like this, it's very promising. You may notice if we look at values, positive or negative, and evaluate x and 1 over x to the 2/3 power, that's something like 0.01. Right? If we square that, that's 0.0001. And if we take the cube root of that, I don't know where I have it written down. I don't have my calculator on me. But you're going to end up with something relatively small. Right? 0.01 to the 2/3 power is going to be, let's see, 0.01 is 10 to the -2. So it'll be 10 to the -4/3. 1 over that is 10 to the 4/3 power, which is somewhere in the ballpark of 20. You know, good enough for our purposes. If I look at 0.001, that's 10 to the -3. Raise that to the -2/3 power, and you get 10 to the -2. Right? I'm sorry, and then -2/3 would be 10 squared, which is 100. And if we get smaller numbers still, this will continue to grow. If you look at negative values, you will get the same repeating process in the other side. So there's some evidence that the limit as x approaches 0 of 1 over x to the 2/3 power is going to tend towards infinity. And we said that when f prime of 0 tends towards infinity, that means that the tangent line is going to be x equals that value c. So in this case, the tangent line at x equals 0 is x equals 0. So there's how, and there's why. And now it's your turn. Going back to what we were looking at earlier, I would like you to take a look at the function g of x equals x squared plus 5x plus 6 over x squared minus 9. And identify each discontinuity of this function and classify those discontinuities as either removable or asymptotic. See where you can get with that, and I'll see you in the next video.